Now, specifically speaking, what have we done for City and Xpeng? Actually, we can look at it from two dimensions. I think the first dimension is the capability of handling different urban conditions to deal with complex traffic environments, including various traffic participants, including ourselves as part of the road condition. The first example is that we have added some lateral control capabilities in city scenarios. The most common thing that you may see on a daily basis is quick cut-in. Now, in this case, you have two options. The first is to brake really hard, and the other option is to do a lane change. We have seen from the slide here that there was a very beautiful lane changing action, slowing down slightly, leaning to the side. I think this is really the city scenario 101. And the second scenario is also very common that requires a lot of negotiation, especially when we are driving at a low speed. If you want to change lanes or if someone else wants to cut into our lane, the situation requires some negotiation between the two parties. In this case, we would call it an interactive structure that we introduce. In this case, we have introduced in an interactive structure into our algorithm, especially in terms of the prediction of nearby vehicles and in the planning of our own behavior. We will not only predict what the vehicle will do next, but also how they will react when we do A or B. In this way, we will be able to gather all the information, make a comprehensive judgment on what we should do next. And the third scenario is also very common, which is handling uncertainty. Now, for example, this car has been driving along the lane. Does it want to cut in or not? So in this case, we are trying to predict each vehicle around us, in addition to giving some certainty to that kind of behavior. Now, it's very likely that the car is going to stay in their own lane, but it's also possible that they are going to cut into your lane. To make deterministic predictions and uncertain predictions, we call it caution, which means that we are going to differentiate different predictions. The priority is to maintain the highest level of safety. So with that premise, we try to make the driving experience as comfortable as possible. And that has been reflected on the latest update on our software that Xpeng has seen for the past few months. And all the steps are embedded in the details. An important aspect of our behavior, our capability of handling, is to react to different mapping situations. One example is that when you have a static obstacle on the road, this may be only a temporary small change to the map, could be some traffic cones or water barriers. Then in this case, we need to allow the car to execute a sidewalk as soon as possible, and then again, we need to make the experience as comfortable as possible. Of course, there are some more difficult scenarios. For example, the maps that we're using may look completely different from the actual traffic scenarios due to road construction or renovation. In that case, we will detect what is happening and we will downgrade to LCCL function using our cameras to pass the road. After passing that part of the road, we'll return to the city and GP. Coming up in our next session, when we talk about our full scenario, I'm going to go into the details of how we make such a switch between different modes so seamlessly that the user or the driver doesn't really feel it. Right now, it still creates some obvious physical sensation during the switch. The third situation related to the map is actually some big intersections. At such intersections, it has a big issue, which is that most of them are not marked. And when we are driving past these lanes, we have to fall back on our usual driving habits. There may be some virtual lane lines in the map, but if you follow this geometric trajectory to drive through these virtual lane lines, there may create some big issues. Therefore, in such scenarios, we will completely erase the geometric information on the map, and according to what we call the traffic flow on the spot, or according to the driving state of the vehicle, analyzing the logical relationship between each lane to determine what we should do. Therefore, as you can see from the slide here, that in the urban scenarios, the core capability is lateral movement. It is very often said that assisted driving or autonomous driving on high-precision map is like driving a tram. In fact, what I would like to tell you is that it is impossible to use the logic of a tram to develop CDNGP or high-level assisted driving in a city scenario. If you want an analogy, you can imagine that the rails of the trams are still there, but there's only rubber bands that are connecting different vehicles on the rails. The rails can tell you where you should go logically, but the core capability of CDNGP is to determine how far off you are from the actual track of the tram based on the perception capability of the car. Now, to describe the developmental process, I think arduous would be an understatement. We started pushing the function to our employees on September the 17th, and after the first week of October, on October the 8th, we launched a public beta test, which means that we make the function available to our car owners in Guangzhou. And a couple of days ago, we made available our next iteration of the software across the country. Such a powerful function must be backed by a very strong system capability of autonomous driving. As we mentioned earlier, on Orin, a hardware platform that we use for our flagship G9, we have done a very big upgrade of the sensors and the central processor of computing, especially for the ECU, which has been upgraded from the original 30T to 500T, a nearly 15 times increase in capacity. At the same time, we have also made a corresponding overhaul on the software, so to speak, especially to support the coverage of unmapped city roads. We have also improved our overall AI capabilities as well. At the same time, under the waterline of the iceberg, in fact, in the past few years, including in the coming 1 to 2 years, we will strive to create a so-called fully closed-loop, self-evolving AI data system as well. Coming up, I'm going to give you more information systematically. Well, let's start by talking a little bit more about our software capabilities. In terms of our software capabilities, the main thing that we're going to do, as mentioned earlier, is to launch our new generation of perception architecture, which we call XNet. Unlike the previous generation of software, where we have the AI capabilities based on single frame of multiple cameras to do deep learning, neural network, and then through a lot of logic and algorithms and computing, and with the fusion of information, we are able to produce 360-degree perception. But for XNet, the keyword is multiple camera and multiple frames. We will inject the video streams from each camera directly into a large model of deep learning network and directly export static and dynamic output in 3 dimensions. Especially for static environment, we'll have super powerful environment perception ability. Simply put, it's like we will have the ability to generate high precision map in real time. On the picture here, you can see a simple example. We are looking at a car passing a traffic circle, which is this cute little red car that we have here. Now you can see that the lane lines here, they are not from high precision map. They are generated by our real-time perception output from XNet. It's not just the lines, it's all kinds of other things that you are looking at. Stop lines, sidewalks, etc. So in the future, we will be able to utilize this to overcome the unmapped scenario and conduct high-level urban assisted driving. We also have a stronger 360-degree perception for dynamics. In fact, for our first generation of perception fusion architecture, we encounter some challenges. You may not expect that the most difficult places is where it's the nearest to the car, because in the place closest to the car, for us, no matter what sensor we use, there are blind spots. For LiDAR, there's a blind spot close to 1 meter. Millimeter wave radar also has a large blind spot in close proximity. And the camera has a distinct boundary in many places because of its dependency on single frame and single camera methods. With XNet, we are doing the equivalent of a pre-fusion dynamic object detection. Now, we can see that a significant improvement of our capability focus on recognizing a near-vehicle object. We believe that we will have more stable near-vehicle object detection, which means that our negotiation capability will be stronger, and your success rate of lane change will be higher as well. For our dynamic XNet, it actually has an impressive ability. What is this about? It not only is able to detect the position of the object, it's also able to detect the speed of the object and even a prediction of the future trajectory of the object, which is very impressive and powerful. Especially for millimeter wave radars that usually have some weaker spots and scenarios, especially in near car area where we have some vehicles crossing in front of the car or from other lanes, it would be very difficult to detect, especially the lateral speed of those vehicles. But with dynamic XNet, we can actually detect the speed of these objects without difficulty, which is a huge enhancement to the millimeter wave radar. Then where the original millimeter wave radar may already be powerful, we can actually create redundancy. By doing so, we can improve the overall safety for our urban scenario. Such a powerful XNet is backed by the latest transformer-based network architecture, but it's actually very difficult to deploy such a network on our software. Let me share some figures just to give you an idea. The first one is labeling. In order to train such a video input network, we may need about 500,000 to 1 million short videos, of which the number of dynamic targets may be hundreds of millions or even billions. According to our statistics, based on our current annotation team's efficiency, we estimate that this could be a workload of 2,000 person-years. What does that mean? For our current 1,000 people team, this may require an entire team's effort for 2 years straight. Completely unacceptable. Then from another point of view, training. Even with one of the best servers, the training time for a single machine takes almost a year. And then, even if we do not do any optimization, if we just directly deploy the network on Orin, it will require more than one Orin, even though one Orin its computing power is already very strong. It requires more than one. So how can we meet such a challenge and be able to deploy the network of large models smoothly? As a result, we have done a lot of work in the past 6 months. The first one that we deploy is our fully automated annotation system. We have improved our annotation efficiency by 45,000 times through our algorithm. The original 2,000 person-years of work through our system can be completed within 17 days. This is very astonishing. I would like to highlight that this auto-labeling capability is not only used in our data collection, where we have a modified wearable 360-degree lidar on the head with point cloud data. We can also use the system to label all the data returned from our current front-mounted mass-produced vehicles cameras. So this is very important for us. In terms of training, we have officially announced a while ago that the largest autonomous driving computing center in China has commenced operation. It's called Fuyao. We partner with Ali Cloud on Fuyao, and Fuyao has a computing power of 600 petaflops. You can see it as putting together thousands of Orin on one single training platform. And we can actually reduce the training time of nearly a year, 276 days, to 11 hours, which is a 602-fold increase in training capacity. And finally, a word about deployment. In fact, we just mentioned that XNet requires 122% of the computing power of one Orin. First of all, Transformer is a very new operation. that has very little support available even on the Orin platform. We got it through our Savior platform, and we can say that it's a deployment that is very unique. And we have a lot of accumulation in the deployment experience, so we did a complete reconfiguration of the whole transformer operation. And we have got basically 2.9 times higher gains in the overall runtime through the reconfiguration of transformer. But if you look at the transformer, which is the green layer in the middle, it is about a 20-fold reduction of its computing time to 5% of the original. In addition, we have a 2.6 times acceleration of the computational deployment through the model pruning. And finally, we have a 1.7 times acceleration through a collaborative optimization between each GPU and DLA. So we took the original computer power that required 122% Orin, and we did it with 9% computing power. Now, we have just talked about how our overall XNet is implemented on Orin, and then XNet is a very significant algorithm for our next upgrade from CityNGP to XNGP. But behind this, I would like to actually talk about our fully closed-loop self-evolving AI and data system. Now, for a closed-loop data system, you probably have heard that there are about 4 important steps: collection, labeling, training, and deployment. And just now, we have already talked a lot about labeling, training, and deployment through XNet implementation. And in terms of data collection, actually, we have nearly 100,000 cars that can be used to complete such a task. And we have made a lot of effort in the past 2 years to complete this closed loop. Now we have deployed over 300 triggers in our user's car, and you can go ahead and determine what kind of corner cases is useful to our system and then upload them. And we can even decide what kind of data we need to collect each week from the fleet by our cloud deployment. And the data source include visual, dynamic, static objects outside of the car, and also full stack data. In the past 6 months, we have made a major upgrade to our closed-loop data system for basic capability improvement, so this may seem much more complicated. I would like to highlight 3 things. The first one is the golden backbone model in the middle, which we have introduced in the past 6 months. And it is probably one of the most important innovations. With the introduction of Golden Backbone, we can now form a small closed loop on the right side, because Golden Backbone is based on a combination of self-supervised and unsupervised capabilities. As long as there is data coming in, the right loop will keep optimizing the base network. With such a base network, another advantage is that we can decouple the improvement of the basic network capability and the training of the release model. So when we need to release the model, we can use the existing base network to do a small amount of optimization instead of using the training from the beginning. If we can decouple these 2 parts, we can get a greater improvement in efficiency. Now, the second change, as you can see here, is the ability to generate simulation data. Our simulated data is as good as authentic data, and we can collect more corner cases. Later on, I'm going to give you an example. The third point is also very important, which is that once we have such a large amount of data, we will also use the actual data to do large-scale data simulation and continuous integration to help our software keep iterating forward. Later on, I'm going to give you more explanation. All right. Next, I will give you 1 or 2 examples to illustrate how this closed-loop data is done. If our test car or our user's car discover that our network may have an undetected case, by the way, this is just an example. This problem has long been solved, so don't worry. Now, this example can be only seen maybe every 1,000 kilometers or 10,000 kilometers, but in fact, in Guangzhou, this is quite common. So I'm really impressed by the innovation of our drivers here in Guangzhou because they can utilize the loading capacity of this tricycle fully. But when our network first sees the case, it would be very surprised. So this will be recognized as a corner case recorded into our system. And then with this corner case in, we would be able to do a dynamic deployment in the cloud to find or locate similar photos. Now there are only 9 photos here. We don't want to overwhelm you, but actually it's very easy to spot this kind of photos in Guangzhou with thousands of similar scenarios, all added to our database to complete the entire model training and solve the corner case, by the way. Now, this is a very simple and straightforward example of how we use data to complete the corner case solution. All right, next, we'll probably look at a more extreme example. Now, this is slightly exaggerated, but it's a real case from the data that we collected from our fleet. At least from my personal experience, I've never encountered this kind of case. I don't know about you, but this is probably once in a million kilometers. This is a big truck. It's got a wheel off, and there is some friction that caused a fire on the wheel. So with such an example, suppose that there is a corner case. How do you actually solve it? Even if we deploy 100,000 vehicles to collect the data, it may take several years to collect enough data. So this is where our simulation capability comes in. Now, this is based on our current UE engine. You can see here that our UE engine is actually used to make Hollywood movies. It really can fake the real, and it can be presented to us with multiple camera views completely together, and it actually has more to offer, which is that it has ground true value, which means that we know where the car is, we don't have to annotate. With such a capability, we can generate thousands of similar cases with all kinds of vehicles with their wheels off. Now, with this kind of capability, we can get a good solution for some of the rarer corner cases, which may be cases that we never encounter at all. In addition to our large-scale simulation verification and continuous integration capability, well, by the way, these data are actually real data. In fact, every line of code change we make before we merge it into our main code base, they have to go through simulation tests of 50 million kilometers, because we know that it's very costly to have rejected or returned code. We definitely do not want our fleet to be unsafe on the road. We need to avoid some low-level errors as much as possible. So we run the codes to verify the change through the 50 million kilometers test. And also, we have 5,000 core scenarios that they must pass. We also have a library of over 17,000 special scenarios. These cases may or may not pass. We'll determine through a comprehensive set of indicators, and it's through this simulation capability that we can have our code and our overall software capability continue to iterate forward.